based drug design. Okay, here we use the same methodologies like structure based approaches, but the initial search space is not a chemical database, it's a fragment database. So fragment database is a small molecular small database. Okay, in terms of size of the library, it is small, and the individual molecules are also smaller than the normal drug-like molecules. Okay, so now we take a fragment library, we screen it against various binding sub-pockets of a protein and get some fragment hits. And now we join the fragments by the link method, grow and or merge method, which we are going to discuss in the upcoming slides. And then we get target specific hits. Then the downstream process is similar as your structure-based drug design. Okay, so let's see first what is a fragment. Fragment is nothing but a small molecule. Okay, so it's a low molecular weight, and it's moderately lipophilic and highly soluble organic molecules. And typically their molecular weight is between 100 to 300 daltons, and it has weak binding affinity for a target. And once these fragments are screened against various binding sub pockets, then uh, they are combined or grown into full drug-like molecules by following several steps. Okay, so since they are part of, I mean, they can construct a larger molecule, lead-like molecule. Most of the lead-like molecules that are present can also be broken into smaller components or fragments. Okay, so this is about the fragments. Okay, and like we have a drug likeliness rule or Lipinski's rule of 5 for a molecule to qualify as a drug-like molecule, we also have a rule of 3 which was given by Congreve et al. So the rule is derived after analyzing the hits from various fragment screens, experimental screens. Okay, it states that the fragment should have a molecular weight which is less than 300 daltons and preferably less than 250 daltons as per the recent papers that I was going through. And the number of hydrogen bond donors should be less than 3. The number of hydrogen bond acceptors should be less than 3. And some of the additional filters also which give more desirable fragment-like compounds are the number of rotatable bonds in the fragment should be less than or equal to 3, and the polar surface area should be less than or is equal to 60 angstrom square. So we see all these cutoff values are multiples of 3, so it is popularly known as rule of 3 for fragments. Okay, so whenever we try to make or try to create a fragment database, we can apply these filters, right? So now what is the advantage of a fragment based drug design as compared to the typical structure based design? Okay, the first thing is higher hit rates. Okay, so they are low in since the fragments are low in molecular weight, and their chemical complexity is also they are also less complex. So uh, they occupy the target sub pockets within the binding site in many ways. Okay, so large molecules, if we screen a large molecule, if we look at this, suppose this binding site can bind this particular fragment, and we are screening this receptor with larger molecules, lead-like molecules, then what happens is some molecules like this will be prioritized as hits. Okay, but when we screen the fragments for separate binding sites, we get specific fragment for that particular binding subpocket, and later we can link it to get a more target specific binding. Okay, then the next most important advantage is chemical diversity space. So the chemical diversity space is better covered with fragment based drug design. because we need smaller fragment libraries. Okay, we don't need molecules, we don't need a library having millions and millions of molecules. Okay, if we compare the fragment space and the lead like molecule space, it is around the difference between them, their size is around 10 to the power 16. Okay, if there are some 30,000 fragments that are there in the chemical space, in the fragment space, then there are millions, around 16 millions of molecules that are there in the chemical space. So it is always easy to start with a fragment library which is smaller in size. We have less number of simple starting points. Okay, so with this, according to the requirement of the binding site, we grow molecules, and we can generate many, like as many as molecules possible with these fragment hits, and they are based on the requirement of the binding site or more specific. Okay, so that's why they have high scope for multidimensional property optimization due to their smaller complexity, and we get high binding efficiency per atom also, because the fragments are very small in size, so they can explore various subpockets, different subpockets in a protein, as compared to the larger molecules, or the lead like molecules with higher number of heavy atoms. Okay, for example, allosteric sites are there. There is a binding protein binding site, and there are several adjacent binding pocket which may be important for ligand binding, or which may provide some binding hotspots. Okay, so bigger molecules cannot enter those smaller pockets, but the small fragments can do. So this is also an advantage of the